Okay, welcome back everyone. In our final video of this unit and of electricity and magnetism in general, we're going to be talking about LC circuits and also RLC circuits. So RLC circuits aren't something that you typically see on an AP test, but they're really interesting and we at least want to talk about them a little bit. But we'll begin with LC circuits. So an LC circuit has an inductor and a capacitor, hence the LC. But it's different from the RC and the RL circuits because it behaves more like a simple harmonic oscillator. If you imagine that you have a mass on a spring, but instead of using mass going back and forth, you're using current. So the energy is kind of bouncing back and forth. And we've talked about how energy can be stored in a capacitor as 1/2 CV squared. And we've talked about how energy, so this is the energy, this is U of a capacitor. And we also talked about how energy can be stored in an inductor, 1/2 Li squared, which is U inductor. And this kind of reminds us of kinetic and potential energy of a mass on a spring, right? That has potential energy of 1/2 kx squared that converts back and forth to 1/2 mv squared. And in fact, what happens in an LC circuit is that you typically start with one type of energy, maybe UC in the capacitor and none in the inductor. And then what happens is after, so this is energy, not versus time, just a bar graph. After an interaction, which is basically current flowing through the circuit, then the energy becomes stored in the inductor. And so what's going to happen is that the current is not going to decrease exponentially in this kind of a circuit. It's actually going to be sinusoidal. So it's going to bounce back and forth. So LC circuits are really interesting. And we start, as always, with an application of Kirchhoff's laws. We know that the inductor has negative L di dt, and if we recall, the voltage drop for the capacitor is Q over C. Now this is something that we haven't seen for a while. You may not even recognize it at all. But di dt is actually the same thing as d dt of I. But what's I? Well, that's dq dt. And you math people out there will recognize that this is the second derivative of charge with respect to time. So aside from slapping positive signs on these, I could write this as d squared q dt squared plus 1 over LC times Q equals 0. Now I'm just dividing through by L for a reason that you'll see in a minute. Okay, now this is going to look familiar if we take the 1 over LC term and bring it to the other side. Okay, all right, how does this look familiar? This doesn't look like anything I've ever seen. Well, it actually does. Okay, so think about a mass on a spring. Okay, so horizontal motion, and F for that is going to be equal to negative kx. But wait a second, F is also equal to ma. And a is d squared x dt squared. And we covered this when we talked about oscillations, but if you weren't here for that, another way to write acceleration is the second derivative of position. So that's equal to negative k times x. So now if you look at these two equations, you should see a similarity here. If we divide each side by m, I'll just do that, then we get d squared x dt squared is equal to negative k over m times x. And so we have the exact same thing mathematically with LC circuits as we do with a mass on a spring. And if you remember, the solution to this was very easy. It was x as a function of time is equal to a magnitude, or a amplitude if you will, times the cosine of omega t plus phi. Now phi is a phase angle, we don't worry too much about that, but omega was defined as the square root of k over m. Likewise, charge as a function of time, so in other words, k over m was omega squared. Likewise, 1 over LC is going to be omega squared, so that means that charge as a function of time is going to be equal to an amplitude times the cosine of 1 over the square root of LC times time plus a constant. That's pretty awesome. So that tells us what I said previously, that the current and the charge are going to be oscillating back and forth between the two components of this circuit. And typically what we say is that this A right here is actually the total charge Q that's available in the circuit. Okay, so that's really all I want to say about LC circuits. Now let's take a little time to discuss LRC circuits. Okay, so most components that you see on a regular basis will have all three of these devices. And mathematically what they do is they combine characteristics of both RC and LC circuits. So from LC circuits, they have a simple harmonic motion aspect, that the energy and the charge is bouncing back and forth. But because of the resistor, there's an exponential decaying term. The resistor is taking that energy and converting it into other forms. Okay, so the current is going to oscillate, but it's also going to die out. It's kind of like a mass on a spring that converts kinetic to potential energy, but it's losing energy to friction. And now this derivation is something that's beyond the scope of this class. It's something that you do when you take differential equations. But we can talk a little bit about where it comes from. So here's your basic LRC circuit, and there's different types because since we have 3 elements, you can have 2 in parallel and 1 in series. We're just going to start with the strict series version. We won't even talk about other versions, okay? And so we have everything here, okay? L d squared q dt squared plus r dq dt plus q over c equals the voltage from the battery. Okay, and so this is EL, this is ER, and this is EC, or if you will, VR and VC. And we've talked about all these terms, but now this is a little bit crunchier. This is what we call a second order differential equation because you have a squared term right here. Now, when we just had the LC circuit, we didn't have this middle term, we just had Q over C, and that's a very easy equation to solve as we just showed. But when you do have this middle term, then it gets a little crazy. And here's one example of a solution. It's just one type of solution for an LRC circuit because it really depends on how R compares to L and C. And we won't get into the details of that, but for this one we're going to do something where the resistance is fairly low. And so this is kind of like a mass on a spring that's able to bounce back and forth, but at a fairly slow rate. So this is our equation. And as promised, we have an exponentially decaying term, and that sort of tells us about this envelope right here. But we also have an oscillating term, which is contained within that envelope. So these get fairly complicated, and just like regular damping in when we talked about harmonic oscillators, you can have underdamped, overdamped, all sorts of damping terms. We're not going to get into the details. We just want to appreciate that once you have all 3 types of these components, that circuits can start to become very complex, and we need some pretty intense math to analyze them. Okay, so we're going to wrap up here, and I hope that you've enjoyed this series of lectures on electromagnetism. And if you haven't already seen them, you should go back and check out the lectures that I've done on mechanics. Thank you for your attention, and we'll see you next time.